Course 3, Industrial Processing, Food Processing Technologies, and Automation. Good morning, everyone. Welcome to today's training module on monitoring, regulating, and troubleshooting key parameters in food processing operations. Over the next hour, we will explore how temperature, pressure, and timing directly impact food safety, product quality, and operational efficiency. By the end of this session, you will understand how to identify deviations, implement corrective actions, and document your findings according to HACCP and GMP standards. Let's begin. This module delivers an in-depth understanding of key food processing methods, exploring their influence on product quality, safety, and sustainability. Learners will acquire knowledge of classical and emerging processing technologies, examine their impact on nutritional and sensory food attributes, evaluate safety considerations including microbial and chemical hazards, and discuss sustainability implications such as energy use and waste reduction. This content prepares learners to critically assess processing choices within modern food systems. After completion, learners will be able to monitor, regulate, and troubleshoot key parameters in food processing operations, e.g. temperature, pressure, timing, to ensure process efficiency, maintain product quality, and minimize losses. Let's think about why we focus on these three parameters. Temperature is perhaps the most obvious. It is the primary tool we use to kill harmful bacteria and to slow down spoilage. But it also affects how enzymes work. Some enzymes that preserve nutrients may be inactivated by heat, while others that cause browning or softening are accelerated. Pressure plays a role in sterilization, in high-pressure processing, and in packaging, where it controls the protective atmosphere around the product. And timing, the duration of exposure, is just as crucial as the intensity. A short burst of very high heat is different from a longer exposure to moderate heat, even if the total energy input is similar. Together, these parameters determine whether we produce a safe, stable, delicious product or a compromised one that could harm consumers or waste raw materials. Temperature is our primary weapon against microbiological hazards. When we pasteurize juice or milk, we are using validated time-temperature combinations, 72 to 75 degrees for 15 to 20 seconds, that are proven to reduce the target pathogen population by a specified log value, typically a 5 log or greater reduction. If we cool the product below that temperature or shorten the holding time, we risk allowing pathogens to survive. Conversely, if we overheat, we may preserve safety perfectly well, but we will lose valuable nutrients and alter the sensory quality of the product in undesirable ways. Cold storage, around 4 degrees, slows both microbial growth and enzymatic spoilage, which is why we refrigerate perishable foods. The key is to find and maintain the sweet spot, the validated process condition that kills pathogens while preserving quality. And we do that through careful monitoring. Pressure is less obvious than temperature, but it is equally important in certain processes. High-pressure processing, or HPP, uses pressures of 400 to 600 megapascals, that is about 4,000 to 6,000 atmospheres, to inactivate pathogens and spoilage microorganisms without heating the product. This preserves heat-sensitive nutrients and sensory properties, making it popular for fresh juices and ready-to-eat foods. In retort sterilization, we combine heat and pressure. We heat to 121 degrees inside a pressurized steam vessel, which raises the boiling point of water and allows us to reach the temperatures needed to destroy bacterial spores, which are far more heat-resistant than vegetative cells. In vacuum and modified atmosphere packaging, we control the pressure and gaseous environment around the product to minimize oxidation and microbial growth, extending shelf life significantly. If pressure is too low, protection is inadequate. If it is too high, packages can rupture or products can be squeezed out. So precise pressure control is essential. Time is perhaps the most misunderstood parameter, but it is absolutely critical. Microbial inactivation is not instantaneous. It follows kinetic laws. We describe this in terms of log reductions. A 5 log reduction means we have killed 99.999% of the target microorganism. To achieve that, we need to hold the product at the target temperature for a specific amount of time. That is the holding time. If we shorten the holding time without raising the temperature, we achieve a lower log reduction and the risk of survival increases. If we extend the holding time, we overprocess and waste energy and nutrients. In drying, the time determines how much moisture is removed and how that affects the final texture and shelf life. In fermentation, time controls how much sugar is converted to acid or alcohol, defining the flavor profile. In curing or smoking, time allows salt or smoke components to diffuse into the product. So timing is not just a parameter, it is a critical control point that must be carefully validated and then consistently maintained during production. A critical control point, or CCP, is the cornerstone of HACCP, Hazard Analysis and Critical Control Points. It is a step in your process where you can exert control and where that control is absolutely necessary to ensure food safety. Not every step is a CCP, only those where control is essential. For pasteurized milk, the heating step is definitely a CCP because it is where we inactivate the pathogens of concern. For canned vegetables, the retort is the CCP. For fermented products, the temperature and duration of fermentation is the CCP. But a step like receiving raw materials, while important, is typically not a CCP because the hazard control happens downstream. Each CCP must be scientifically validated. That means we have conducted studies or reviewed literature to confirm that our chosen parameters, say 72 degrees for 15 seconds, will reliably achieve the log reduction we need for safety. That validation is your justification for those parameters, and it is what inspectors and auditors look for. Let us talk about the tools we use to monitor these critical parameters. For temperature, we have several options. Thermocouples are fast and can be integrated into continuous systems. They work by measuring the voltage generated when two different metals are joined and heated. Resistance temperature detectors, or RTDs, are very accurate but respond more slowly. They measure the change in electrical resistance of a metal as temperature changes. Infrared thermometers allow us to measure surface temperature without touching the product, which is handy in some situations but cannot measure internal temperature. Thermistors are small and sensitive, often used in probes or sensors. Whichever sensor we choose, we must install it at the right location, typically the cold spot or slowest heating point, so we are always measuring the worst-case scenario. And we must calibrate it regularly against a known standard, perhaps every few months or whenever we suspect it is drifting. The data from these sensors is typically logged automatically in modern systems, creating a permanent record for compliance. For pressure, we use gauges or transducers. Gauges give us a visual reading but require manual recording. Transducers convert the pressure into an electrical signal that can be automatically logged and displayed on a control system. Like temperature sensors, pressure instruments must be calibrated against a certified standard. Many pressure systems have a tendency to drift over time, especially if they are exposed to frequent pressure spikes or vibration. For timing, we rely on timers and clocks. In a batch process, we might manually start and stop a timer. In a continuous process, we calculate residence time by dividing the vessel volume by the flow rate. If a pipe holds 100 liters and product flows through at 100 liters per minute, the residence time is 60 seconds. Modern systems log all of these data points automatically, creating a record that can be analyzed for trends and reviewed during regulatory audits. The frequency of monitoring depends on the nature of the process and the risk. For a pasteurizer or a deep fryer where the product is moving quickly through a heat exchanger or a heated vessel, conditions can change rapidly, so we monitor continuously, perhaps every 5 to 10 seconds, and the system automatically adjusts or alarms if temperature drifts. For a fermentation tank where the product sits for several days at a controlled temperature and agitation, we might check the temperature every few hours or every 12 hours. Continuous monitoring would be overkill. For storage, we might spot check temperature once or twice per day. The key is to match the monitoring frequency to the rate at which the process can change and the consequence of missing a deviation. A pasteurizer needs continuous monitoring because a 1-degree drop in temperature could affect thousands of liters in minutes. A cold room holding finished product can be checked manually daily because the environment changes slowly. One of the most important aspects of modern process monitoring is data logging. Rather than simply observing a gauge and mentally noting that it looks okay, we capture the actual value at each moment and store it. This creates a record that can be reviewed if there is ever a question about whether a batch was produced safely. If a customer complains or if there is a recall, you can pull the log and say, here is exactly what temperature and time this product received. It is also evidence that you are controlling the process and complying with regulations. Beyond compliance, data logging gives us information. If we look at the temperature trends over weeks or months, we might notice that the pasteurizer is gradually drifting to a lower temperature, which suggests that heating element efficiency is declining. We can schedule maintenance before a failure occurs. Remote monitoring, cloud-based systems that let supervisors view the plant from home or from a different site, adds another layer of efficiency. Alarms can be sent to a phone, allowing faster response. Some systems even use predictive analytics to forecast when a sensor might fail or a part might wear out, allowing preventive maintenance rather than waiting for a breakdown. Many food processing systems use a PID controller to maintain critical parameters automatically. PID stands for Proportional Integral Derivative. It is a control algorithm that works like this. The controller reads the current temperature from a sensor and compares it to the desired set point, say 73 degrees. If the actual temperature is 70 degrees, there is an error of -3 degrees. The proportional component of the controller responds to that error by increasing the steam flow. The bigger the error, the bigger the adjustment. But pure proportional control often overshoots the target, so the integral component watches the accumulated error over time and makes fine adjustments to eliminate steady drift. And the derivative component watches how fast the error is changing and anticipates whether the temperature will overshoot, reducing the input to prevent that. Together, these three components create a smooth, stable control loop that keeps the temperature at the set point despite disturbances like a sudden increase in feed rate or a drop in steam pressure. PID control is so effective and reliable that it is used in thousands of food processing plants worldwide. For larger operations or multi-product facilities, SCADA systems provide integrated control and monitoring across the entire plant. SCADA stands for Supervisory Control and Data Acquisition. Imagine a dairy processing facility with multiple pasteurizers, cold tanks, and packaging lines all running simultaneously. Without SCADA, an operator would need to walk between machines, reading gauges and noting temperatures. With SCADA, all the data from all the sensors is transmitted to a central control room. A single screen shows the temperature of each pasteurizer, the pressure in each tank, the fill level of each product line, alarms from any equipment, and historical trends. If the temperature in pasteurizer number 3 drops below 72 degrees, an alarm sounds, a message appears on the screen, and a text is sent to the operator's phone. The operator can see the trend and make a decision. Is this a temporary fluctuation or a sign of a failing heat exchanger? Meanwhile, the SCADA system is automatically logging all of this data into a database, which can be printed or exported for audits. For a plant operating under HACCP or ISO 22000, SCADA is almost essential because it creates the documentation that regulators expect. Every operational limit must be grounded in science. We cannot simply decide that 70 degrees sounds good. We must have evidence that it is sufficient for safety. The starting point is usually literature, peer-reviewed research on the thermal inactivation of target pathogens in your product. For example, research might show that E. coli is inactivated at 71.7 degrees Celsius for 1 second in orange juice. But you do not set your limit at exactly that temperature because there is measurement uncertainty. So you add a safety margin, perhaps 0.3 degrees, and set your operational limit at 72 degrees. You might also have a research minimum, say 15 seconds, to account for the time it takes for the whole batch to reach thermal equilibrium in your equipment. You then document this reasoning in your HACCP plan. You also validate that your measurement instruments, thermometers, gauges, timers, are accurate enough to reliably achieve the operational limit. If your thermometer has an uncertainty of plus or minus 2 degrees, setting a limit at 72 degrees is meaningless because you cannot be sure the product actually reached that temperature. So calibration is essential. Even in the age of automation, operators remain essential. Many smaller operations do not have fully automated control systems, and even large operations have situations where an operator must take manual action, perhaps during startup, shutdown, or if a sensor fails or the automated system is offline for maintenance. A good operator understands the equipment, knows what parameters to watch, and knows how to make adjustments. If the temperature is dropping, the operator might open a steam valve gradually, watching to see how the temperature responds. They know that it will not respond instantly, there is a lag, so they do not make huge adjustments that will cause the temperature to overshoot. They understand that if the holding time is too short, they can either slow the flow or extend the holding vessel residence time. They know to record each action they take in the process log for traceability. And they have been trained not just once but regularly with refresher training and scenario-based exercises so that muscle memory and decision-making are reliable. This is why operator training is listed as a key component of every HACCP plan. When a deviation occurs, the first thing an operator must do is confirm it is real. A single off-color reading might be sensor noise or a momentary blip, not a true process deviation. So we look at the trend. Is the value consistently low, or was it just 1 point? If we have multiple sensors monitoring the same parameter, we might check them all. If the temperature sensor on a pasteurizer suddenly reads 65 degrees, but the product coming out of the system still feels hot, and the downstream sensors show normal temperature, the upstream sensor might be faulty. Once we confirm a real deviation, we look at the trend. If the temperature has been slowly drifting downward over weeks, that suggests a gradual problem like a heating element losing efficiency or a sensor calibration drift. If it suddenly dropped 5 degrees, that points to something that failed. A heating pump stopped, a valve closed unexpectedly, or steam pressure suddenly dropped. We ask, what changed? Did the feed rate increase? Was the ambient temperature very cold yesterday? Did maintenance recently work on the system? Often, the cause becomes obvious once you remember a recent change. For more complex deviations, we use structured methods like fishbone diagrams, drawing branches for different categories like equipment, people, materials, environment, and listing potential causes under each branch. Or we use the 5 whys. If the temperature is low, why? Maybe because heat supply is low. Why is heat supply low? Maybe the steam pressure is low. Why is steam pressure low? And so on, until we reach the root cause. When a CCP deviates, a protocol must define immediate actions, stop production, divert affected product, alert management, investigation, confirm the deviation and identify the root cause, corrective actions, adjust equipment settings, repair/replace parts, recalibrate sensors, product disposition, decide whether affected product can be reprocessed, must be discarded, or can be sold with disclosure. Prevention, implement measures to prevent recurrence, e.g., preventive maintenance schedule, operator retraining. Every food company must have written protocols that define what to do when a CCP deviates. These protocols are part of the HACCP plan and are signed off by management. Let me walk you through a realistic example. A pasteurizer temperature drops below the operational limit of 72 degrees. The protocol says, immediately stop feeding product into the pasteurizer. You do not want more product to pass through at low temperature. Divert any product that is currently in the pasteurizer to a holding tank, not to the finished product storage. Alert the supervisor or shift manager immediately. Then investigate. Is the thermometer reading accurate? Check it against a backup thermometer or a calibration standard. Is the steam pressure low? Look at the steam supply gauge. Is the heat exchanger fouled? Maybe there is scale or biofilm reducing heat transfer. Once you identify the cause, you take corrective action. Maybe you increase the steam set point, or you realize the heating element is faulty and needs replacement. While repairs are ongoing, you need to decide what to do with the product that was exposed to low temperature. Depending on how long it was at what temperature and what the target pathogen is, you might be able to reprocess it, run it back through the pasteurizer at correct conditions. Or if the time-temperature combination was far below safety, you might have to discard it. The protocol should outline the decision criteria. And finally, you implement preventive actions. Perhaps you schedule preventive maintenance on the heating element monthly, or you train the operator more frequently on recognizing steam pressure drops. Documentation might seem like paperwork, but it is absolutely essential. In food safety, you have probably heard the phrase, "If it is not documented, it did not happen." When a regulatory agency audits your facility, or if there is a recall investigation, your process logs are the only proof that you were controlling critical parameters. If you had a deviation and you corrected it, your deviation report and corrective action record show that you took appropriate action to protect consumers. Without documentation, even if you did everything right, you have no evidence. Beyond compliance, documentation gives you data. Over months and years, you can see trends in your process. Maybe the average temperature drifts up slightly each month, suggesting that your heating element is becoming less efficient. Or maybe you notice that deviations are more common on Tuesdays. Maybe it is the day a certain operator is on shift, suggesting a training need. Maintenance records show you which equipment components fail most often, helping you plan maintenance strategically. Calibration certificates prove that when you recorded a temperature of 73 degrees, the thermometer was accurate within its stated tolerance. So documentation is not a burden. It is your map of the process and your proof of control. For shelf-stable products, keep records for the shelf life of the product plus 1 additional year. Let me illustrate how parameter control directly impacts the real world. First, imagine a milk pasteurization plant where the operator does not monitor carefully and temperature drifts to 68 degrees. Listeria monocytogenes, which can cause serious illness in pregnant women and elderly people, survives that temperature. The contaminated milk is distributed to supermarkets and homes. Some consumers become ill, some seriously. The company discovers the problem when it receives complaint calls and hospital reports. An investigation traces it back to the milk. The product is recalled, shelves are cleaned, the brand reputation is damaged, and the company faces litigation and regulatory action. Now, the opposite problem. A plant manager, worried about safety, decides to heat the pasteurizer to 80 degrees and hold it there for 2 minutes, just to be extra safe. Safety is achieved, but the heat damages vitamin C, causing flavors to become oxidized and flat. When consumers taste the juice next to a competitor's product, they prefer the competitor. The extra heating saved nothing, it just degraded quality. The economic loss is real. Finally, imagine an herb drying operation where the drying temperature is too low or the drying time is too short. The final moisture is still 12% instead of the target 8%. The herbs feel soft and slightly damp. Within a few weeks, in the humid storage environment, mold grows. The entire batch must be discarded. These examples show that control must be precise, not extreme, and science-based, not guess-based. Let us talk about money. Proper control of critical parameters is not just about food safety, it makes financial sense. Consider a product recall. If a batch of 10,000 units is found to be unsafe and must be recalled, the costs are substantial. Removing product from shelves, destroying it, notifying consumers, regulatory reporting, investigation, and potentially legal settlement. For a small or medium-sized company, this can be hundreds of thousands of euros. Beyond the direct costs, the brand reputation suffers, consumers lose trust, and sales fall. If a facility has multiple recalls, it can go out of business. so recall cost is severe. Beyond safety, overprocessing costs money. If you overdry herbs, you are wasting energy. If you overheat juice, you are consuming steam and degrading quality without benefit. If you undercontrol, products spoil in storage, leading to waste. On the flip side, good control saves money. Proper moisture control in dried products extends shelf life, reducing spoilage in storage and in distribution. Optimized pasteurization time reduces energy use per liter while maintaining safety. Consistent process conditions mean less waste and more sellable product. And there is the compliance cost. If an inspector finds deviations and poor documentation, the facility might be ordered to shut down for remediation, a very expensive proposition. So, in summary, good control of critical parameters is an investment that saves money through reduced waste, reduced energy use, reduced spoilage, reduced risk of recalls, and reduced regulatory risk. Process control gaps. Measured values show significant gaps. Temperature, 70.8 degrees Celsius, is 1.2 to 4.2 degrees Celsius below 72 to 75 degrees Celsius range. Pressure, 14.2 pounds per square inch, is 0.8 to 5.8 pounds per square inch below 15 to 20 pounds per square inch. Processing time, 28 minutes, is 2 minutes below 30 to 60 minutes minimum. Humidity, 58%, is 2% below 60 to 70%. All four parameters deviated, indicating systemic issues rather than isolated faults. Deviation effects: microbial safety, under temperature and short time reduce log kill. Pressure low affects flow sterilization efficacy. Product texture: low humidity causes drying, cracking. Short processing prevents proper gelatinization. Flavor: incomplete processing retains raw off notes. Excess moisture risk from poor control. Shelf life: combined deviations enable spoilage growth, shortening from months to weeks. Corrective actions: assessment actions, steam set point increase, pump checks, were effective as parameters recovered post-adjustment. Timeliness good, implemented within 5 to 10 minutes of detection via alarms, limiting affected volume to approximately 15% of batch. Prevented escalation to full shutdown. Loss correlation trends, gradual temperature pressure drift, correlate with spoilage losses. 300 to 1,000 euros per batch. Safety risks, recall costs 10,000 euros plus. And inefficiencies, downtime 30 minutes, energy waste 20%. Total potential loss, 2,500 euros plus per incident. Monitoring. Role: continuous monitoring ensures HACCP compliance, Codex standards. Data logging supports audits, traceability. Sustainability benefits: reduces waste, circular economy, energy use, precise control, and emissions. Improvement recommendations: upgrade to IoT sensors with predictive analytics for early drift detection. Implement SCADA for automated alarms, PID control. Monthly preventive maintenance, heat exchanger cleaning. Operator training on 5 whys troubleshooting. Target 0 deviations quarterly. Let me summarize the key points of today's training. First, every operational limit for every critical parameter must be based on science. You should be able to cite a research paper or a regulatory standard that justifies why your jam is heated to 90 degrees for 30 minutes, not 85 degrees or 95 degrees. Second, you must monitor consistently, using sensors that are calibrated and recorded. For a CCP, continuous monitoring is typically necessary. For less critical steps, batch monitoring may be sufficient. Third, when a deviation occurs, you must act quickly. Every minute that a pasteurizer runs at 68 degrees instead of 72 degrees produces more contaminated product. Fourth, when you troubleshoot, use systematic methods. Ask why something happened, then ask why that happened, 5 times if needed until you reach the root cause, not just the symptom. 5th, document everything. Your process logs and corrective action records are your proof that you are controlling the process and your defense if anything goes wrong. 6th, invest in your operators. They are the eyes and hands of your process. Train them well, retrain them regularly, and create an environment where they feel empowered to raise concerns and suggest improvements. And 7th, treat your process data as a valuable asset. Review it regularly, look for trends, and use those insights to make your process better. Food safety and quality are not in conflict. They are two sides of the same coin. Good control of critical parameters achieves both. Thank you.